All right, well, good morning and happy Friday, everyone. It is, oh wait, I have this numbered wrong. It says week 5 Friday. It's week 4 Friday. Getting ahead of ourselves. That's like, is it really week 5? No, it's week 4 Friday. I'll get that fixed later. Okay. Today we are going to cover some more topics from Numpy. Again, Numpy is the package that we load into, or the library, or the, I don't know, module that we load into Python that allows for us to use the Numpy array, which is a data structure where everything in the array has to be of the same data type. And that helps speed up computations. If you try to do math operations with a list versus math operations with a NumPy array, you'll find that the computations for the NumPy array are much faster than the computations for a list. So anyway, let's take a look at some more things that we can do with NumPy arrays. All right, and so our first thing will be for concatenating arrays. And so here I've created two arrays using the arange function. But I mean, just let's say I've got any two arrays. These are one-dimensional arrays. Okay, and so here I've got 0, 1, 2, 3, and 100 through 103 over here. These are just two one-dimensional arrays. And if you just call concatenate, this will concatenate it on the only dimension that exists, right? So there's only one dimension, so it's basically a line, and then you've got basically another line. And if you ask to kind of join two lines together, it's only going to just make it longer. So you got 0, 1, 2, 3, 100, 101, 102, 103. Okay, there is an argument for access for when you do NP concatenate. The axes are 0 indexed, and so this would be equivalent NP dot concatenate. Again, there's only one axis at this moment in time, so we can call axis equals 0, and it would be exactly equivalent. All right, let's try to concatenate in the other direction. Okay, so if we say, hey, concatenate not along this way, but in the other direction, it actually throws an error. Okay, now why does it throw an error? Well, there's no other dimension, right? So when you ask for the shape of one of those arrays, okay, 0, 1, 2, 3, its shape is a tuple of length 1. Okay, and so this is the 0 index dimension. The 0 index dimension is its length, and there's nothing for there's no 1 index, axis 1 indexed value there. Okay, so there's a couple ways to deal with this. One is you could call a function called Hstack. Okay, numpy.vstack, and this will vertically stack two unidimensional arrays. So it'll take 0, 1, 2, 3 and vertically stack it onto 101, 10, the other array, and it will return a 2-dimensional array. So this will be a 2 by 4. The shape of this is 2 by 4. Another option is you could reshape this. You can reshape the array X. Okay, and you can do X dot reshape into 1 row, 4 columns. And so now this is a 2-dimensional array, and we can reshape the other one, and we can call concatenate on this. So if I concatenate on axis 0 here, axis 0 is the number of rows, right? So if you think of the shape of this, it's 1 by 4, and so axis 0, it would be the 1, the number of rows, and and axis 1 would be the number of columns, the 4. So here, if we concatenate along axis 0, we're appending rows together, and we're going to get a 2 by 4 array. Yeah, so in a 2D array, the 0 index is for rows and the 1 index is for columns. And so here, if I take the same thing, X reshaped into a 1 by 4 array and Y reshaped into a 1 by 4 array, and I say concatenate on axis 1, we get, it extends the number of columns from 4 to a total of 8. All right, does that kind of make sense how the concatenate works here? All right, so here we've been calling NP concatenate, and when we call concatenate, we basically provided a list or a tuple of the arrays that we want to concatenate together. All right, so we can further extend this. And so here I've got two two-dimensional arrays, okay? I've got XM kind of representing X matrix, YM representing Y matrix. Both of these matrices are 2 by 3 arrays, and thus we can call concatenate. So yes, the shape of X matrix and shape of Y matrix are both 2 by 3, and we can call concatenate on these things. So the default behavior of concatenate is to concatenate along axis 0, which is the number of rows. So it takes our 2 by 3 and it concatenates the 2 by 3. And so now the result is a 4 by 3. But again, you can specify the axes yourself. Okay, again, axis 0 will concatenate against the index 0, which is rows. Axis 1 will concatenate along index 1, which will be the number of columns. And so we would end up getting a 2 by 6. All right, so same behaviors, just for something that for the 2 by 3 matrix. Okay, now other the function that we saw earlier, Hstack, which worked for the 1-dimensional arrays, also works for 2-dimensional arrays in exactly kind of the way you would expect. There's also the equivalent called Hstack. So you can take that and it will stack them horizontally. And so this might, Hstack and Hstack, this is kind of like your R bind and C bind that we have in R. And then concatenate is just kind of a generalized version that works for actually any higher dimensional, any dimension array, right? So you could actually have a 3-dimensional array and concatenate along axis 2 or axis 3 or something like that. And you could kind of imagine how that's going to work out, right? And so you can always use Hstack and Hstack to kind of concatenate vertically or horizontally. So let's talk about math operations, okay? So math operations with Numpy arrays behave pretty much the way I think you would expect them to behave, right? So if I take an array 0, 1, 2, 3, and I do x plus 5, it's going to add 5 to each element. What Python does is it's what we call broadcasting. It's kind of the equivalent concept of recycling. So in R, it recycles values across a vector. And in Python, it does something called broadcasting, or NumPy, it broadcasts, and it takes this value and it creates a kind of an equivalent array of the same size filled in with the same number. And then it adds that, okay? And if you take X and you add Y, it adds them element-wise. So 100 plus 0 is 100. 101 plus 1 is 102. 102 plus 2 is 104, and so on. So these behaviors are I think exactly what we'd expect them to be. X times Y, again, element-wise, multiplication. So we get 0, 101, 204, 309. And then you can call sum. So you can take the product here of x times y, and then you can say, hey, I want the sum of these 4 elements together, and it does exactly what you expect them to do. Okay, there is a regular old sum function, which will also work. And then there's the Numpy sum function. And the Numpy sum function is actually is optimized to work very quickly for NumPy arrays. So numpy.sum, and it's more noticeable when you have a very big array. Numpy.sum will be fast. So that will be my recommendation, is to use numpy.sum. Okay, you can do the dot product of two kind of not vectors, but if you think of your one-dimensional arrays as vectors, then the dot product is pretty much the you take the elements, you multiply them together, and you add them up, right? So it's the same thing as multiplying x times y element wise and then adding them up, and that would give us the dot product. That is what you get when you apply it to two vectors or two one-dimensional arrays. Okay, you can also do matrix multiplication. The at operator is matrix multiplication, and here we're doing a one-dimensional. We've got one-dimensional arrays. So how can you do matrix multiplication with one-dimensional arrays, or these vectors here? And pretty much it's just doing the dot product. So we're all getting 614 when we basically do 0, 1, 2, 3 dotted with 100, 101, 102, 103. So we get 614 here. This is kind of doing it quote manually, and we got np dot dot and x at, or x matrix multiply y also yields 614. All right, before I forget, let me give you your first view quiz answer for today. Today's first view quiz answer is the letter B, B as in bear. B as in bear is your first view quiz answer for today. Okay, so let's revisit these two-dimensional matrices. Okay, so again, we've got these 2 by 3 matrices, xm and ym, 2 by 3. And so again, we can do +5, and it broadcasts the 5 into an equivalent 2 by 3 matrix and adds them all up. You do x plus y, xm, ym, and it does element-wise addition. And I don't think that's a surprise at all. Okay, so just for us to review, if you do xm times ym, we will get element y's multiplication. So 0 times 100, 1 times 101, 2 times 102, and 5 times 105 yields 525. So I think this is all perfectly fine. There is np.multiply. Okay, there's another function called dot multiply, and this is basically the same operation as the asterisk or the star operator. The star operator is also, star operator's element-wise multiplication, and numpy.multiply is also element-wise multiplication. I think all of these things also come with, you can also do xm.multiply ym. And although I don't have it at this, let's just, let's open up, let's delete everything out of here. Let's just clear out this. Okay, so let's do this, and we'll do, oops, I'm in command mode. All right. Okay, so we got xm equals a range. Reshape. right, so I think I can do xm dot multiply as well. Oh no, you cannot. Okay, never mind. I lied. Okay, so there's xm dot. Well, let's ask for help. ND array. So what are the you can ask for the transpose. These are all of the attributes. So anytime you have an object and you're not sure what you can do, okay, you can ask help on that, even the object name itself, and Python will recognize, okay, this is an ND array object, and it will tell you these are some of the different different things we can do. And okay, there's a whole bunch of things. Let's see. So we've got the dot product. We've got max, mean, min. These are all kind of functions that we can apply. Reshape, resize, round, set field. Okay, I guess no element-wise multiply listed here. Okay. So I saw on CampusWire there's a question. How do we know when it's like np dot, when it's some kind of function and you put in the arguments there, or if you do xm dot something? And the answer is you just kind of have to learn. There is kind of some structure and idea and concept of how these things work together, but it's also it's just part of the vocabulary. When you learn a new language, how do you remember the word? What is the word for coffee maker? What's the word for this or that? And it's just, you just kind of have to learn some of that vocabulary. And that's just kind of how it is with Python. Is some of these things you have to remember it goes this way, and some of the other words it goes, some of the other functions go another way. Okay, but anyway, we talked about element-wise multiplication. We can now do matrix multiplication. All right, and so here we can take xm and take ym transpose. Okay, because when you do matrix multiplication, the number of rows in matrix A has to match the number of columns in matrix B, and so I would have to take ym and transpose it, and then I can do that, and then so I'd have a 2 by 3 multiplied by 2 by, what did I say? The number, okay, I had that wrong. The number of columns in matrix A needs to match the number of rows in matrix B. I would have a 2 by 3 matched with a 3 by 2 after I transpose it, and then the result will be a 2 by 2 matrix. Okay. This one you can, with the dot product, you can do xm dot dot, okay, and you can multiply it by ym transpose, okay. And again, the dot t, the transpose, is just an attribute of the Y matrix. So we can do xm dot dot, ym dot t, and then you can also just use the matrix multiply operator, the @ sign, and you can do xm matrix multiply ym dot t, and all of these things will yield the same results. All right, let's look at some basic math operations. So again, x is going to be a vector 0, 1, 2, 3. We've done the +4, we've done the -5. Here's multiply by 2. Okay, no surprise here. We're just kind of taking all of these things and doing exactly what we would expect. Okay, anytime you do division, you're going to get floats. You can also do negative sign, and it will turn everything negative. You can do powers, okay, and raise everything to the second power. So we're squaring everything. You can do modulo division, and this will give you the remainders. And you can also ask for absolute values, right? So this is all fine and dandy. We have some trig functions. And so here I'm going to create a vector from 0 to pi. I want 5 elements. So this is 0, this is 1/4 pi, 1/2 pi, 3/4 pi, and pi, right? So this is spaced out by quarters. So you think of the, what is this? 45 degrees, 90 degrees, 135 and 180 degrees, the equivalent in radians. All right, and so you have a bunch of trig functions. Now, these trig functions also exist in the library math, so we could also import math, and we could do math.sine. But if you are dealing with NumPy arrays, again, all of these NumPy functions have been optimized to work with NumPy arrays. Okay, they'll also work with oh, now I'm worried if I'm going to tell you something wrong. But I mean, so you could use math.sine and it will work. But the NumPy functions have all been kind of optimized to work with NumPy arrays, so you'll get faster performance. And so you can call the sine function on this array of theta values. Okay, so sine of 0 is 0. Sine of pi halves is root 2 over 2. Okay, and then sine of sorry, this is pi over 4 is root 2 over 2. Then you get 1, root 2 over 2, and this is pretty much 0. Okay, this is the floating point equivalent of 0. Anytime you see a floating point number where you're getting e to the negative 16, that's pretty much 0. Okay, it's just like some kind of calculation thing. We couldn't quite get it down to 0 exactly, and that's what we have. Cosine is just the opposite, right? 1 root 2 over 2. Here we got 10 to the negative 17, so the equivalent of 0, negative root 2 over 2, and negative 1. Okay, and then tangent. Okay, so what do we have here? We have 0, 1 for pi halves, and then I'm sorry, not pi halves. Pi over 4 is 1. Pi over 2, it's not quite infinity. Okay, it's 10 to the 16, and that's a far cry from infinity. But I think this is just a limitation of dealing with a rounded off number here. But we can see it gets really big. Okay, it shoots up, and then we get something. We get negative 1, and then we get something close to 0 as well here. So again, not quite infinity, which would be the theoretic value of tangent, as I mean, I guess depending on whether you are approaching from the left or right, right? So it goes, it shoots off to positive and negative infinity right around pi over 2. Okay, the exponent functions and log functions also behave exactly as we would expect. So here I've got 1, 10, 100. The log function is always the natural log. So we would get 0, 2.3, 4.6, whereas you can call for the common log, and this will be numpy.log 10, and you'll get 0, 1, 2. Okay. You can also ask for the exponentiation, the e function, and so you can do a numpy.exp and any kind of values here, and so 0, 1, 2 gives us 1 e and e squared. There's also there is the exponentiation function for powers of 2. So you can do 2 to the 0, 2 to the 1, 2 to the 2. And then there's also just the power function, which is just any arbitrary number raised to the y power, okay? Or any arbitrary value raised to any other arbitrary value, okay? So 3 to the 0, 1, and 2 squared gives us that. So these are all kind of exponentiation functions, which are handy. We've got sum and we've got numpy.sum. Numpy.sum is faster than sum, but there are a few quirks here in that they might not always give you what you want. So here I've got the integers 0 through 99, okay? And if you were to sum them all up, you're going to get 4950. So what's that? 99 times 100 divided by 2. That's kind of your rule for, right, n times n plus 1 over 2. So indeed, we get 4,950. And if you do numpy.sum, you get the exact same value. Okay, and both of these things yield the same results here. Okay, so that's fine. For a one-dimensional array, sum and numpy.sum behave exactly how we would expect. There is a function called time it, okay, and it takes a while, so I didn't run this, but I will come over here. Let me so I'm going to create a big array of random values, 10,000 random values, and we're going to time how long it takes to use sum, all 10,000 values, and how long does it take to do numpy.sum. And so percent time it runs the same operation multiple times, timing it, and then and it takes a little while. And so here it says to use sum. The operation takes 863 microseconds plus or minus 15.6 microseconds per loop. Okay, versus using numpy.sum, each operation took about 5.85 microseconds. So this is much faster. Okay, versus the other one. This one's 863, and this is over 100 times faster. Right, it's 5.85. So even if I multiplied 5.85 times 100, it would take less than 863. So, and I don't know how fast your computer is. You can try this operation. And I don't know, I built my computer in 2020. I don't know. I don't even know what chip I have in here. What is it? It's a Ryzen something. I think my computer's decently fast. Oh, something happened here. Uh-oh. All of my slides stopped operating here. Okay. They didn't render. What happened? Oh, that's weird. Let me try this again. Save this. Into slides. So seconds ago, menu browser tab. Okay, so here we go. Okay. All right. All right, I gotta update that. And well, I'll push my changes to GitHub after class. But for now, you'll just have to look at my screen. And I'm sorry, it didn't the version that I pushed, it didn't have the values rendered. Okay. You can also ask for the minimum and the maximum value. So, you know, this is just, these are just random uniform values. I got 10,000 of them. So what's the smallest number and what's the biggest number? And there's also kind of the equivalent, there's min and max just in base Python, and you've got min and max from the NumPy version. And again, if you were to run these things through the timing operation, we'll see that the NumPy version is over 100 times faster than the base Python version. Again, the base Python version is kind of designed to work around a list, which as great of a data structure as it is, it's also not computationally the fastest one because a list has to contain a lot more overhead in memory because the list has to contain information about what type of data each element in the list is, because the list could have different types of data in the thing. And so, so computationally, a list is a much less efficient data structure, even though it's very, very convenient and truly powers a lot of stuff in Python. Lists are great, just they serve a different function. Okay, so you can do you can take this two-dimensional structure, right? So we have this this two-dimensional structure here. It's a 3x4 matrix, and this I just got by doing a range, and then I called shuffle. You can take our matrix, and we can do and I just did shuffle, and then I reshaped it into a 3x4 matrix. When you call sum, Python's sum base sum function, it's going to sum them column wise. Okay, so it's going to do 2 plus 1 plus 11, 3 plus 6 plus 9, 4 plus 0 plus 8, and we get column wise sums. Whereas when you call the Numpy function, it's going to sum all of the elements in the matrix, all 12 values, and you get 66. Okay, so there are some behavioral differences between base Python sum and numpy.sum. And to me, numpy.sum makes more sense than, I'm not quite sure why the default behavior of sum in base Python is to do column addition here. Now, certainly you can do column addition in with numpy's sum function. You just specify. You specify I want to add along axis 0. Okay, so axis 0, again, axis 0 is the rows, and axis 1 is the columns. And so here you're saying I want to add across the rows. It will sum over the rows. So 2, 1, and 11 get added, 3, 6, and 9 get added, and we are summing across the rows, across axis 0. You can also do numpy.sum axis equals 1, and it will sum across sum across the columns, and you'll get 3 values. The sum of the first row, 2, 3, 4, is going to be 19, 4, 33. So we're summing across axis 1 across the columns there. Okay, and then similarly, you can find you know, column-wise minimum and column-wise maximums, or row-wise minimum. So any of these kind of aggregate functions, you know, finding the sum or the min or the max, you can also apply the axis argument. Otherwise, it's going to find the sum of all the elements, or the minimum of all the elements, or the maximum of all of the elements. Okay, let me go ahead and give you your second view quiz answer. Today's second view quiz answer is A as an apple. A as an apple is our second view quiz answer. Standard deviation function, we'll take the standard deviation of all the elements, apply an axis argument, and it finds the standard deviation across that axis. Same thing with the mean function. You can find the mean across the row. What is the mean of these values? What's the mean of these values? What's the mean of these values? Okay, what if we have a higher dimensional array? All right, so here is a 3-dimensional array. Okay, this is a 2x3x4. I've got 2 sheets, 3 rows, 4 columns. Here I've got just a number 1. Okay, and so again, when you specify an axis, you can kind of one way to think of this is you can think of it as collapsing that axis. Okay, so you can say, let's collapse axis 0, right? So again, when we specify the axes or the shape of a higher dimensional array, 2x3x4, okay, the index 0 axis, okay, is that is the number of sheets. And so when we specify axis equals 0, it's going to collapse. It's going to collapse axis 0, and we'll be left with a 3x4 matrix. Okay. Similarly, if I specify axis equals 1, okay, we are going to collapse, or we're going to sum across the rows. All right. And so what are we going to end up getting? All right, we're going to end up collapsing the rows. So all 3 of these rows will get collapsed, and but we still retain the fact that we have 2 sheets and 4 columns, and so we're going to get what do you call it? A 2 by 4 matrix full of the element 3. Okay. And then I guess this one got cut off. You can, you know, it's going to do exactly what you expect it to do. It's going to sum across the columns, collapse the columns. So with floating point numbers, inherent to the floating point number data structure is a value called nan, right? And so, you know, nan is any kind of value that arises when, you know, there's no kind of mathematical result. And you can get the nan type created directly by calling float and putting nan in quotes, and this will instantly create a nan value. And but it's still a floating point object. Okay, so so that's what we have now. In NumPy, there's no designated NA. So in R, which is I think one of the fairly unique things about R as a language, is that there is a designated missing value for every data type. There's an NA for logical values, and NA for, you know, string values, and an NA for numeric values. And we don't have something like that in Python. However, the nan kind of serves its purpose of representing missing values. Okay, so you can get nans as the result of some kind of illegal math operation if you try to like do 0 divided by 0 or something. But you can also use it in the place of missing values. All right, so you can get infinity. You can designate infinity using float INF. And then if you try to do any of these operations like infinity divided by infinity or infinity minus infinity, you're going to get nans. Okay, those are undefined. And so if you try to sum, if you try to add 2 to a nan value, you're going to also get nan. All right, and if you try to do but we have the nan sum, which is kind of the nan safe version, and that basically says do the sum, but just ignore any nan values. Okay, so ignore any kind of missing or nan values, and so it's going to say, okay, the sum is just 2. It's kind of like the equivalent of doing na.rm equals true, and these all kind of, and they're all like just nan in front of the word. So you got np.sum and you got np.nansum. And so the total, you know, you got sum, product, mean, standard deviation, var, and all of these things. You know, if nan is one of the values in the array that you're trying to compute, all of the regular functions will return nans. Whereas if you want it to kind of ignore the nan, then it will ignore the nan. If you do the nan version. So you got np.nan standard deviation, nan var, nan min, et cetera, et cetera, et cetera. Okay. All right, and the okay, now we have to get into this topic of broadcasting. Broadcasting is similar to the concept of recycling values in R, but you know, in R, there's kind of like you know, you can do have mismatched dimensions, or you know, you could take one vector of length 5 and another vector of length 8, and it will recycle even though they don't quite match up. And basically in Python it just says no, we don't play that game. So so here I've got A and B, and this adds things element wise. 1, 2, 3 added 4, 5, 6 added element wise. Whereas if you try to take something of length 2, I've got a length 3 and I'm trying to add a length 2, it says no, you can't add, you can't take this thing of length 3 and add something that's length 2 together. So it's going to just kind of, you know, R would have recycled this. It would have done 7 plus 8 plus 7. It would have recycled those values around. And Python says no, we don't do that. Okay. All right. So watch what happens here. I've got this vector, or not this vector, this one-dimensional array, 1, 2, 3, and I've got a 3 by 3 matrix, 1, 1, 1. So when I do E plus A, this 1, 2, 3 vector, or this 1, 2, 3 array gets broadcast across the rows. Okay, so it basically converts the 1, 2, 3 array into a 3 by 3 matrix by duplicating the rows, and then it adds it up. And so we're going to have two 3 by 3 matrices to add together, and we have 2, 3, 4, 2, 3, 4, 2, 3, 4. All right, I can reshape A into a column. And then if I say E plus A, then it broadcasts A. So to match kind of the dimensions here. So again, this is 3 by 3, and this is 3 by 1. It's going to broadcast this so that it matches kind of the structure, and we get 2, 2, 2, 3, 3, 3, 4, 4, 4. Okay. When you do Hstack, or I'm sorry, here I have a 2 by 3, and I can do this, and it does exactly what I would expect it to do. It'll add 1, 2, 3 across the top and 1, 2, 3 across the bottom. No problem there. If I have this length 2 vector, and I have this 2 by 3 matrix, okay, and then I say do D plus C, it complains and it says this doesn't have compatible dimensions. Because again, it's looking at this and it's saying this is just length 2, and this is 2 by 3, and it complains, right? It says this thing is 2 by 3 and this is length 2. These don't have compatible dimensions. So what we have to do is we have to reshape this into a 2 by 1, a 2 by 1. We have to reshape it into a column, okay? And then it will allow, okay? It will allow us to broadcast it, and it will add 7 across the top, and it will add 8 across the bottom. Because we will reshape this. We're basically turning this into a column, 2 by 1 column matrix, and then we can broadcast the 7, 8, the 7 across the top and the 8 across the bottom. This is something interesting that happens, okay? So I am taking E. E is going to be a 10 by 1, 10 rows, 1 column. F is a length 10 array, and I can actually add these two together. And this seems strange, right? So the shape of this is 10 by 1, and this is 10 comma. And what this does is it looks at E, it looks at F, and it says, can I get these into compatible objects that are compatible with each other? And it says we could. If we take this and we broadcast it, one for every row, I'm sorry, one for every column in here, and we take this thing and we broadcast it, the result will be this gets broadcast into a 10 by 10, and this will get broadcast into a 10 by 10, and we can add those two 10 by 10 matrices together, right? And so so basically we get the sum of all of these values here. Or actually, this is I'm sorry, this is length 11. Okay, so this gets broadcast into 10 by 11, and this also gets broadcast into 10 by 11, and we get a 10 by 11 matrix here. And similarly, if you do star, it will do kind of the multiplication. It broadcasts them, and it does element-wise multiplication. And here we've created basically your times table from, you know, 3rd grade that we had to create. Here is you know, here's D, okay, and I can reshape D. Remember, you can take some kind of matrix, right? So this is 2 by 3, and you can use something like reshape. And here I'm going to reshape this into a 1 by 6 or a 6 by 1. So we can take each of these elements, and if I do 1 by 6, we're going to get a column 1, 2, 3, 4, 5, 6. And if I reshape it into a 6 by 1, we're going to get, I'm sorry, 1 by 6 is 1 row, 1, 2, 3, 4, 5, 6 across, and 6 by 1 is the column 1, 2, 3, 4, 5, 6 down the column. And so I can reshape these and add them together. And after reshaping them, these we've got this 1 by 6 and we're asking it to add a 6 by 1. It's going to broadcast them again into a compatible 6 by 6 matrix and add them together. This is kind of this behavior of broadcasting a row or a column into a full matrix it might be one of the stranger things that we experience or witness in Python, but it is quite useful and handy, and so you might see these kind of operations being used when you read someone else's code, and I don't want you to be shocked or surprised by these results here. Okay, I'm going to run out of time. Well, before I forget, let me go ahead and give you your last view quiz answer. Today's last view quiz answer is the letter C. C as in cat. C as in cat is your final view quiz answer for today. C as in cat. Okay, Boolean operators. So this, you can do basic comparisons and it will return a bunch of Boolean values, these kind of true false values. And this behaves exactly, I think, as one would expect. Which elements in our array X are less than 3, which elements in our array X are greater than or equal to 3, which ones are exactly equal to 3, right? And so these things behave exactly as such. You can then take that Boolean array and use it to subset. Use it to subset your array X. So we can do array X subset on X greater than or equal to 3. And it subsets to the values that are true, okay? You can also ask, you can apply sum to a Boolean array, and trues get turned into ones, falses get converted to zeros, and this will basically give you the sum of how many values are true, as well as you can call the mean, and we'll give you the proportion that's true. This operator, the tilde, is the negative, the opposite. So if it's true, it becomes false, and false becomes true. This is the negation operator for Boolean values. It feels strange. We're often accustomed to like using the not exclamation point or something like that, but it's the tilde in Python here. Okay, so which values are not equal to 3, and that's what we get. What just happened here? Oh, this is okay. If you leave off the parentheses, this will say not X, which values not of X. So X, it doesn't quite work out. Okay, and basically tilde X turns everything into kind of its negative. Basically multiplies it by -1 is what's going on here. Okay, you can also do the same kind of Boolean things with matrices. Okay, which elements are greater than or equal to 6, and you can ask for the sum, and you can do row and column wise sums as well, and things like that. So I think that's fine. There are you can do element wise Boolean element-wise Boolean operations. So, you got the true, true, false, false. So you have the and sign, ampersand, and the or. And these only work basically with Numpy operators, okay? Otherwise, if you've got like an if statement, okay, you should spell out the word and or spell out the word or. And you've seen that, you've already kind of used that when you were doing kind of your function programming. So so the ampersand and the or sign here, the symbols for this, these do the bitwise and or, and they get applied to kind of these NumPy arrays. Okay, and then this one's the exclusive or. Okay, I'm going to leave you guys to read the remaining slides. The only kind of section that I'm skipping that I want you to check out is the fancy indexing, and I hope the examples that I've provided will be sufficient as far as understanding what's happening here. Okay, sorry for running out of time, but that will be it. Have a great weekend, and we will see you guys in person if you're willing to come on Monday, January 31. Otherwise, I will continue to record the lectures and I'll post the videos, and we'll see you guys later.